73 seconds after liftoff, the Space Shuttle Challenger broke apart over the Atlantic Ocean. 7 people died. But the night before the launch, a group of engineers sat in a tense, hours-long phone call, looking at their own data, and begged management not to fly. They had the numbers. They named the exact component that would fail. They were overruled anyway. How does the most advanced spacefaring organization on Earth hear a clear warning and proceed regardless? The flaw that destroyed Challenger was understood, documented, and visible on earlier flights. Yet, over years of successful missions, the organization learned to treat a known danger as routine. The shuttle relied on 2 immense solid rocket boosters strapped to the sides of the external tank to get off the pad. Because these cylinders were too massive to build in one piece, they were manufactured in segments. Wherever segments met, a joint had to be sealed. Inside what engineers called the field joint, a metal part called the tang slid into a groove called the clevis, like a lid pressed into a tin. 2 large rubber O-rings sat inside this metal seam to keep burning gas from escaping. But the geometry was flawed. When the booster ignited, tremendous internal pressure pushed outward, causing the metal joint to bend and flex away from itself. Engineers called this joint rotation. Exactly when the O-rings needed to seal the gap, the metal pulled the gap wider. Now add cold weather to the equation. Rubber, when it gets cold, gets stiff. Instead of springing outward in milliseconds to fill that widening gap, a freezing O-ring is sluggish. It takes too long to push back into place. This was a fatal overlap. The metal gap widened at the exact millisecond the chilled rubber was too slow to plug it. Sociologist Diane Vaughan later gave this process a name: the normalization of deviance. It is the slow slide where a dangerous anomaly happens, the system survives it, and eventually the deviation becomes expected background noise. NASA knew about the joint rotation early on. Tests in 1977 and internal paperwork from 1980 explicitly stated that once the motor reached 40% of its operating pressure, the metal bent so far that the secondary backup O-ring was no longer verifiable. Then the actual hardware started trying to warn them. Flight after flight, recovered boosters were pulled out of the ocean, showing erosion. Hot combustion gas was chewing into the rubber. Engineers found soot streaked past the primary seal, proof that the barrier had been breached. A launch in January of 1985 resulted in the worst soot blowby to date. It was a direct physical link. Record-setting cold weather was attacking the seal. The shuttle had sustained damage, but it had landed safely. Because they survived, management reclassified the erosion as an acceptable risk. They were measuring the success of the system by the fact that it hadn't failed yet, rather than the fact that it was broken. That brings us to January 27, 1986. A record-setting cold front pushed into Florida. Overnight, temperatures around the launch pad would plummet toward the single digits, leaving the massive vehicle sitting in 30-degree air at the planned launch time. At Morton Thiokol, the company that built the boosters, engineer Roger Boisjoly and his team saw the forecast and called for an emergency meeting. They drew a hard line: do not launch below 53 degrees Fahrenheit. That was the lowest temperature where they had successful flight beta. NASA managers, facing tight schedule pressures, reacted with dismay. They were accustomed to engineers proving a flight was safe. Now they were being asked to delay based on data the engineers admitted was not airtight, leading one manager to ask if Thiokol wanted them to wait until April to launch. Under that pressure, Thiokol's management called for an offline caucus, asking the engineers to step out of the room. One executive was urged to take off his engineering hat and put on his management hat. The experts who actually understood the rubber seals were no longer the ones making the call. When they got back on the line, the recommendation had flipped. The data hadn't changed, but the burden of proof had. Instead of requiring proof that it was safe to fly, the system now forced the engineers to prove it was unsafe. They couldn't, and the launch was on. The following morning, the physical hardware behaved exactly as the laws of thermodynamics dictated. In the moments after ignition, cameras captured puffs of black smoke pushing out of the right-hand booster's lower joint. The freezing O-ring was too slow. Burning grease and rubber escaped. For a few seconds, byproducts of the combustion formed a glassy slag that temporarily plugged the leak. The shuttle climbed, but about a minute into the flight, aerodynamic wind shear punched at the vehicle, shaking that fragile temporary seal loose. An 8-foot tongue of fire licked out of the side of the booster. It rapidly grew to 40 feet, acting like a blowtorch playing directly against the massive external fuel tank holding liquid hydrogen and oxygen. At 73 seconds, the structure gave way, the propellants ignited, and the vehicle was torn apart. There was no mystery to the failure. In the months that followed, the Rogers Commission was tasked with explaining this failure of mechanics and management to a grieving nation. During the televised hearings, physicist Richard Feynman sat at the commission table with a piece of O-ring material and a small C-clamp. He squeezed the rubber, dropped it into a glass of ice water for a moment, and then pulled it out. When he released the clamp, the material stayed squashed. It had lost the resilience it needed to seal. The technical fix took 32 months. When the shuttle finally returned to flight, the joint had been redesigned with a capture feature to physically resist the metal bending, a third O-ring, and built-in heaters to keep the seals warm. The erosion had been measured. The temperature warnings were clearly spoken out loud. Every piece of knowledge needed to stop the launch existed inside the organization the night before it happened. What failed was the willingness to act on a truth that was standing right in front of them. Disasters of this scale rarely begin with ignorance. They begin with a small acceptance, repeated until no one remembers it was ever supposed to be a warning.